Good evening. Welcome to the English session. How are you doing this evening? Doing good? Are you relaxed? Very relaxed? Well, we're going to be two students that will be coming up in about an hour. Two past students over from my first seminar. And then we're going to play in 10-15 minutes some singing, and one of them sings and the other one plays ukulele. So we're going to have a break of 10-15 minutes, about 9 o'clock. How about that? So we're going to do it like every other time we do it. We're going to go through a few problems from older exams, right? It's the same format like every time we do. So let's look at this. Number one problem. Let's think about it. This problem is asking us to choose the correct diagram, so we really need to figure out enthalpy and internal energy, how it changes as a function of temperature. This one tells us it's not a function of temperature. Here we see that they are a function of temperature. Here they're going down as temperature increases. Here they go up. Between the difference of here and there's a big difference. What is that difference? Huh? Yes, these are switched. What does that mean? We need to answer the question, what does that mean? So each one of them gives us a different idea, right? Independent of temperature, reverse proportional temperature. Here they go proportional, they just go up when the temperature goes up. Here it's reverse. What does this reversing mean? What does this reversing mean? Think about it. If you have a vertical line like this, right, some temperature, it tells us, as you can see from the diagram, that for every temperature, enthalpy is higher than internal energy, isn't it? Yes? You see it? And here it's the opposite. So, that's true. Okay, so what would you choose? A. You would choose A. Why is that? It comes from really there, right? So from that equation, from the definition actually of enthalpy, right? It's equal to U plus dV. You can see internal energy is all the energies, potential and kinetic. Well, that means that with temperature, if you increase the temperature, you increase the thermal content, right? The motion, kinetic energy, so U will go up, right? If U goes up, will this go up? Why? You have something else here too. How about if this goes down? Right? So you have to be careful. You might be right this time, but you always have to be careful. Right? So, if you want to know what enthalpy does, okay, so for you to understand why it will go up, right? We understood that. As you increase the temperature, the internal energy can go up. So, we cannot have this or that. As you increase the temperature, internal energy goes up because it's potential plus kinetic energy, right? Kinetic energy basically goes up if you increase temperature. So we choose one of these two are correct in regard to internal energy is increasing as temperature increases, correct? Yes. Now, how about enthalpy? Delta U is equal to delta X is equal to delta U plus, for an external pressure, in this class we said we're going to always consider external pressure constant. P external times delta V, right? So what happens to H? Does that go also up when the temperature goes up? We said that this goes up with temperature. How about the product P is equal to nRT? Does that go up when temperature goes up? Yes? Everybody knows? You want to explain why? You want to explain why? Raise your hands. PV is equal to nRT, right? So this is constant. We assume it's same amount of material. If this goes up, P goes up, this will also go up, right? Can you see that? Constant, constant, this goes up, therefore this whole thing goes up. So increasing temperature, both increase, right? So enthalpy also will increase. Yes? Okay. So either of them is correct, but now we need to choose between the two. So you can see from this equation that always enthalpy is larger than internal energy, right? So that's why we choose this, because for every temperature you can see internal energy is there, enthalpy is higher. Okay? Should we go to the next? Okay. So here we have this type of problems. You can see them in two different ways. They can talk about what happens to energy or what happens to temperature. So it needs a little bit thinking. So we have a reaction taking place in a solid container. So if you have a material, right, in an isolated container, isolated. So there is no way to have energy transfer in the form of work and heat between the surroundings and the system. Well, this is the system, right? And there's chemicals here reacting and so on and so forth, right? But it's an isolated system. So there's no way to get energy in the form of heat or work between the system and the surroundings, because the chemicals are in that container and surroundings, right? So what it says, before the reaction starts, the reactants are at some temperature X, right? And the products of the particular reaction have higher potential energy than the reactants. Reactants is the initial state of the system, product is the final state of the system, yes? So it tells you that the products have higher potential energy. Before the reaction starts, the reactants are at X degrees Celsius. So initially, we have X degrees Celsius. Initially, the products of the particular reaction have higher potential energy than the reactants. Higher potential energy. So here is reactants, here is products, potential energy. Here, let's say this is energy potential, and this is reactant, this is the product. The problem is telling us we have the products of a particular reaction have higher potential energy than the reactants. Okay? When the reaction is complete, the temperature of the product is higher, lower, equal, or double, whatever than the So what's the answer? Why is that?
Energy is proportional to temperature.
You see, when you have the system, right, the reactant, right, and you have some temperature, whatever, X degrees Celsius, right? So this is the reactant, this is the products. So we have X degrees Celsius, degrees Celsius. We also have a kinetic energy. There's some kinetic energy, whatever, right? Let's say, you can put it any way you want. You can put it all the way up there. Kinetic energy. So the reactants have kinetic energy and potential energy. Let's say this is the relative sizes. We don't know. Maybe this is more than that. it actually interchanges because there's vibrations and for potential kinetic, right? Like the quark, right? So you cannot say this is a value. Approximately, we can say here is the kinetic, here is the potential. And for this kinetic energy, right, other motion has this degree Celsius. And then the reaction is taking place and we have the products. And now the potential energy of the products is higher than the reactant. So this one has become higher, right? So from here it became higher. What will happen to temperature? Because it's isolated system, right? So no energy in the form of work or heat can go in and out. So the energy of the system, which is the internal energy, right? All potential and kinetic together, all this, stays the same, yes? It will be all this together, this plus that, right? Will be the same here and there, because it's isolated, right? So because it's going to be the same, when the potential becomes bigger, the kinetic has to be smaller. Right? Can you see that? This is for kinetic potential. This is the whole thing. It has to be the same thing. The potential became bigger, so the kinetic, which is now this, is smaller than before. Can you see it? And smaller kinetic energy means kinetic energy is related to temperature, so it's going to have new temperature less than X degrees Celsius. Is that cool? Huh? Okay. Everybody got it? Okay, let's see the next one.
Question.
Yes.
Why did the temperature go down if the kinetic